A lot of you know the story that we started this project as a project over 10 years ago when we had industry groups come together, intergovernmental groups come together, and suggest that we should be advancing green roofs in the Lower Mainland, but it was too rainy and the weather was just too nice. So was it really going to be worth the investment? And that's what begat the initial Green Roof Research Project and a facility that was constructed at the Great Northern Way campus. The original funders came from the Greater Vancouver Regional District, the Intergovernmental Water Liaison Groups, Environment Canada, Public Works, and NSERC. And we originally did just focus on storm water and thermal performance. But over time, we developed other expertise as our group grew and started to look at issues around acoustics, plant viability. Green walls started to become introduced, and we had to look at water balance. And then ultimately, urban agriculture, it became a mandate. What kind of material should we be using? And now we're looking at interior focuses on with interior walls and indoor environmental qualities. Who we interact with, well, I thought I'd cut to the chase, just get to how do we get our money and our funding, and say, well, we interact with a lot of industry partners, whether it be through competitive competitive grants, collaborative funding, or unsolicited funding proposals. We typically work with our industry partners, which I've listed on the right for you, to collaborate and advance a project. In terms of the students that we interact with, there are many. We interact with them in terms of having courses. So in order to advance a technology such as green roofs or a living wall technology, you can't just put it out there in the market. You now have to educate within the public realm policymakers, decision makers, and the users and homeowners on how to either install or maintain a green roof. So to that end, we develop courses to respond to the different sectors, and we label them the GROW courses, short for green roofs and living walls. And they range from anywhere from 4 hours to 18 hours to 36-hour modules to advance the technologies. Like many people here on this campus, we do a lot of service lectures. And that means we go into the interior design, or they come to us, architectural building engineering, or resource management students, School of Business and Civil, that have an interest, usually focused on either something like stormwater, if it's the civil engineering group, or the issue of sustainability in the School of Business, or plant viability in the Sustainable Resource Management group. Also, we do our lectures into the UBC programs as well. But it's not just through courses, it's obviously through the research that most of our work has developed. And we've been very fortunate to have a very hands-on applied research approach that allows us to engage with the trade students. And the trade students have worked with us from the very beginning. That original research project was actually built with over 15 different faculty and 200 trade students. And they engage with us in technology projects. So unlike the other speakers here today, I didn't bring my students. They're back at the lab, and one of them's working with ARC2013 in sheet metal, trying to figure out how to grow a tree out of lightweight aluminum structure and counterbalance it with green roof technologies. I should have brought them here though. Okay, so the other thing we do, we have technology-based projects. So that might be with the SRMT students or the ABET students. We have grant-supported student projects that for the past 2 years have been provided to a student in architectural science, but it may expand to a civil engineering student. And then we have our course projects and our thesis projects in our master's degree programs. And I'll detail those projects in a moment. So in terms of a list of projects, it's a sample from the 2011-2013 timeframe. And the first two I'm going to speak about, which is the rainwater interception project funded by a Green Wall Industry Consortium, and a sound absorption of green roofs project funded through Investment Agriculture Foundation, Industry, and UBC. But that also gives you a short list on some of the other types of projects we're still advancing, whether it be with respect to plant viability, different aspects of noise. The one on impact noise through roofs was a fairly novel project completed by a grad student. We also had a two-year diploma student that did, again, a very novel and fantastic project on looking at how living walls reduce reverberation in the classroom in the English building. Some innovative projects on using new materials in green roof technologies to get a lot more form and excitement on the roof level. And then along with Technology Center, Joe Newton's group, we've helped the City of Calgary develop a green roof research site. So the first of the featured projects, and I'm following Antoinette's layout of 2 featured projects in the past and 2 featured projects for the forward. The first one I want to review is the rainwater interception capacity of green roofs. Well, this was green facades. This is quite interesting. Green facades, and I'll just flip ahead to the image. Those are green facades up on our research center. We're being touted as a very scalable, very visual, very biophilic technology that you could put on the front of your possibly very ugly building and start to engage with the public in a more sustainable manner. And there was thought to be some very big benefits on the water balance and the protection aspect for the building. So we said, you know what, let's understand this and let's quantify if there's really a rainfall diversion, something that will actually protect the building system, building envelope system. And we define that by interception capacity. And then if there is, in fact, a rainwater interception, what are the mechanisms of these systems that are allowing for the interception? And then we want to understand how wall orientation and rainfall patterns would affect the capacity of these green facades here to protect the building. So what we had for the experimental setup was the old research center. And we took all 4 aspects, but actually it was only 3 of them that were available to us in the end, to attach different types of green facade systems. Overall, we had close to 400 square feet, which were instrumented with a total of 300 square feet of vegetation. We also had our reference plants as well. So the green facades, just to be really clear, are systems where the plants are climbers, and they climb up either cables or a net that's in tension, or a 3-dimensional rigid grid structure. So the English building has climbers. It actually has great climbers that actually grow up the facade itself. And all we're doing with the green facade is moving it off the building. So putting another structure 8 centimeters, 10 centimeters, 20 centimeters in front of the building. So is that going to help? Having taken these different systems, and you'll see the actual suppliers' names that donated their products and funded us, we took the different systems and we associated with them different types of plant species that were most appropriate for the technology, whether it be a cable or a net system. And then, of course, we had to set up our reference walls. And then we first defined what the interception capacity was. It was simply the difference between the rainfall, which would come off a regular wall, the panel next to it, and the wall which was behind a vegetated screen. So it was the difference between the two. We needed our weather station data, which was on top of the research facility anyway. And then we created micro-weather observations for every facade, for the south, the west, and the east facades, that gave us our wind, our temperature, relative humidity, and other parameters. And then the panels themselves were instrumented in subzones of 3, so the bottom, the middle, and the top, for temperature, relative humidity. And then we devised a system to measure the runoff that was coming from behind the panels. Now what we needed to do is correlate the system in its confounded state with the plant species and the coverage of plants on the system, as well as we defined the coverage in terms of area and in terms of depth. I won't go into the details. And what we end up with is looking at rain events that went from anywhere from our lovely little drizzles of 1 millimeters in a day to 106 millimeters events. And over 87 observations, we were able to see that 63% of the time, we had something we'd call a positive interception. 63% of the time, there was less rain hit the side of the building when you had a screen, which was vegetated. But in actual fact, 37% of the time, there was more rain on the facade, and we had to start to deal with that. What we then decided to call this, we were a bit surprised here. We thought we'd always be shielding the building. It would always be a better solution. But it's not. So the positive interception, this is what is happening when the building is shielded, and we're diverting the rain from the building. That's we think is good, right? But the negative interception, something else was happening. The biomass is collecting the water. The wind is tossing it on afterwards. The biomass was acting as a bridge and directing water directly onto the facade. And with a statistical analysis, and I'd like to credit Caroline Houston for joining us with that, we were able to determine that once you got up to around 34% of vegetation coverage, you were able to move into the realm of, you had a 50% possibility actually, of decreasing the amount of rainfall on your roof, on your wall. But until you got to that high level of coverage, you were actually in the state where you were delivering more water onto your facade. Now with that piece of information, we're armed with some issues here. How do we reduce the physical bridge between the biomass and the facade? How do we protect vulnerable building envelopes? And how do we deal with the fact that we've created a new environment between the green facade and the building that has increased relative humidity, decreased temperature, decreased wind, decreased solar radiation? And we're delivering more rain onto the facade. So we now have to start to investigate a new design of and new guidelines for pinning the green facades onto the buildings. So that was one project. The second featured project was on sound absorption of vegetated roofs. So this was important to look at how we can reduce noise pollution in urban areas and how we can increase the potential to inhabit roofs. So why is that important? Well, I'm just going to go back really fast in history and say we used to use roofs. We lived on roofs. We had picnics on roofs. We had our barbecues on roofs. They slept on roofs. In Algiers, all the fancy people used the rooftops for transportation. And it was the soldiers and the cattle that used the streets. We used rooftops. And when we got in, as far as the 20s, we had Odo's elevator. He had his elevator up there. And all of a sudden, the rich people were accessing roofs. The hygiene precept came out of Dresden that said roofs are a good place to inhabit because the air is cleaner, the views are better. So next thing you know, we had sanatoriums on roofs, we had children's playgrounds on roofs. Then we had a few wars came into place, and so did advancement of mechanical engineering systems. And where did they end up? They ended up on the rooftops. So from the 50s to about now, the rooftops have been relegated to mechanical systems. Now we're in a situation of high density where we have to take back the rooftop and we have to inhabit the roof. But we've created a problem up there. We have a lot of noise. So the idea about using absorption of green roofs to reduce noise is what this project was about. And we wanted to be able to investigate if, in fact, green roofs would reduce noise, which diffracted over the edge of a building, if it reduced noise, which is propagated along the rooftop of the building from a mechanical system. So the first thing we have to do is figure out how to test this. So in an anechoic chamber at UBC, I was able to use a 2-microphone technique in which I used a loudspeaker normal to the green roof, and this is an exact replica of a green roof inside the anechoic chamber, and deduce its overall normal absorption coefficient from a transfer function. And I wanted to first design a system of evaluation and then take it up onto a rooftop. The problem is when I go up onto the rooftop, like this one at the Elevated Research Platform here on campus, is I have all sorts of things. I have parapets, I have dividers between the different green roofs, I have wind. So it first had to be evaluated in an anechoic chamber as a method for evaluation, then went up onto what is now going to become the Elevated Lab and devised 25 different plots of varying depth and plant communities and evaluated their absorption potential. It has to be said that this piece of work was coupled with work using multivariate analysis to predict the normal absorption coefficient of the substrate that these plants grow in. And the results show that relative to a highly reflected roof, which is the lowest line on the graph to the left, we have a marked increase of 20 to 60% of sound absorption because of the vegetated roof. What's interesting is as we increase the depth of substrate, we do increase our absorption. So that was good, but that's just when it was substrate. As soon as we introduced the different plant communities, the data became quite a bit more skewed, and for real obvious reasons, such as the fact that our mosses, our bryophytes that tend to grow in with our sedums, is actually a very short root length, and it keeps the water up to the top surface of the vegetated roof. Whereas plants that allow the water to descend through the depth of the substrate will behave differently in terms of their capacity to absorb sound. Whether it's in the summer or the winter had a significant impact. We certainly have very wet green roofs here. And again, with that amount of rainfall, they're still absorptive in the realms of 50%, or sorry, in the realms of 30-35% in the winter, but in the summer, they increase substantially in their capacity. And what came out after trials of 2 years is that it really didn't matter when you averaged it over the year what type of plant community you use, and we could still look at 20 to 80% absorption of sounds. I think I'll just acknowledge Nicholas Rousseau and Dr. Murray Hodgkins for their assistance on this project, and move on to the next. So the list of future applied research projects. These are the funded research projects that we have. One is the sound living in Vancouver's laneway housing, which I'll detail. A second is a vegetated noise barrier, which quantifies the soundscape. And I'm trying to use very objective acoustical spatial material parameters. So we say soundscape, but it's not way out there. I'm not listening to the sounds of the whales as they move by a vegetated noise barrier, but I'm trying to actually quantify by looking at anthropomorphic and biophony sounds, the different, using different frequencies and FTTs to determine if the vegetated noise barrier will introduce more natural sounds into the environment. The other system, which is quite interesting, is the impact of the living walls on room absorption, reverberation time, and sonic subzones and speech intelligibility, and that's being funded through NSERC Create at UBC. Also in collaboration with Karen Bartlett at UBC, who's also an SPPH, we're looking at indoor environmental qualities, her interest being VOCs, CO2s, and endotoxins. And then I'll highlight the elevated lab. So the first featured project is the sound living, the acoustical quality. What's happened essentially here is we have in our jurisdiction of the Lower Mainland regulations that as you move into multifamily housing, you need to have a certain acoustical quality in your residential unit. So in terms of traffic sounds, you can only have about 45 decibels of traffic sound in your kitchen, 40 decibels of traffic sound in your living room, and only 35 decibels of traffic sound in your bedroom. And to get a permit to advance a CD1 comprehensive rezoning, you have to proof that. And we have processes in place to do that. Well, all of a sudden, we had the Eco-City Density Project. And we decided to densify all of Vancouver. And one of the initiatives was the laneway house. And we're going to place housing in laneways. So we've got a couple issues. We've created high-density dwelling place. They're only 400, 500, 700 square feet. There's no other side of the house to go to. It's no different, really, than living in a multifamily residential building. It's on its own. So they have a how-to guide for how to build a laneway house, and they have a how-to guide for sound living in Vancouver. And the two of them actually have conflicting directions on how to provide a high-quality environmental or acoustical environment. So what we need to do here is evaluate the building envelopes that these houses are being made in, evaluate the building envelopes in terms of sound isolation. Then we have to investigate the actual acoustical characteristics of the laneways. It's very, very different noise types in the laneways. These laneways abut Knight Street. There are laneway houses on Knight Street. So why are we not applying the discussion of the traffic noise on Knight to the laneway? But what happens when you move mid-block? All of a sudden that noise source is no longer a linear traffic noise, but as it moves down through the laneway, it becomes a point source, which has the potential to build up depending on the environment of the laneway itself. The third piece of this was to then investigate the use of green wall systems to change the soundscape within the laneway, to change how that road traffic noise would move through the laneway. The impact on this one is to, I think, address a research gap which connects acoustics to health. Right now, according to the World Health Organization, noise pollution is the leading pollutant affecting cardiovascular stress and cognitive development. We'd like to be able to make recommendations to the municipalities for how we can complement the laneway housing guidelines and the sound living guidelines. We know we can advance the state of practice in terms of how you design that building envelope and how you design that unit layout. And then we know that we can provide an improved acoustical environment and meet the World Health Organization criteria. Those are just some of the images on the laneway house. So the student that's going to be working on this, and the many students that have worked on this project, they're evaluating envelope, they're evaluating noise propagation as it moves through the laneways, whether it's a cottage laneway or whether it's a canyon laneway, depending on what side of town that you're on. And then we have to validate the algorithms and the software that are typically used to predict traffic noise inside a residential dwelling. And then the last, of course, is to then understand the absorptive characteristics of green walls, not unlike those of green roofs. We can use the same type of methods, and to see if, when we feed those into the models, we can reduce the sound traffic noise inside the laneway house. So we have to acknowledge a lot of students that have worked on this one, and most in particular, Rosa Lynn, who's a grad student in the Masters of Applied Science program. So the last project, featured project here, is the new Elevated Lab. So that fantastic research center that we've had at the Great Northern Way has come to its conclusion. We thought we had 4 years. We had 11 years down at the Great Northern Way site, and now it's being rebuilt out as the Emily Carr University. So I had been up on that elevated, we call it the elevated research platform, for about 4 years doing different types of research work up there. And we realize now that we're going to relocate the functionality of the GERF to the elevated lab. So it's 13 times bigger is number one. It's in Burnaby is number two. Most important things is the access to students and the access to other faculties for collaboration. So I'll just run through the, I think, 9 or 10 projects here and show you some images. I'm going to have to flip back and forth. The first thing is when you access the elevated lab from Smith Street on the north sector of BCIT campus, there's going to be a living wall, which is 25 meters squared. And the living wall will be supported by harvested rainwater. Second, there's going to be a green fence. The green fence is a prototype design for planters. And now we do know that there's some new planters running along Smith Street. They're going to be a little different. They're planters which are going to represent some aesthetics of BCIT that we would wish to promote, but as well be projects for students in steel fabrication and carpentry. And the other thing you will see at that base, aside from the living wall and the fence, is a display monitor which will display the real-time data on stormwater and thermal performance. So that's the part about the refunctioning of the Research Center at Great Northern Way to here. Up on the roof level, we'll have the green facades that you saw in the earlier discussion on the stairwells. The upper roofs will be used for research on thermal performance and stormwater, moving over the functionality. We'll have an interactive living wall, which the students will be able to engage with, whether they're looking at particulates or thermal performance, urban heat island, acoustics, plant viability. It won't really matter. The idea is this is infrastructure that is accessible to the School of Construction, and all the other 5 schools that we have here on campus. There'll be an interactive green roof plot where students in the GROW courses will be able to actually get their hands dirty once again, as we did on the Great Northern Way campus. We have a beautiful learning center that was just finished out by Eric Hiob and Steel Fab, which will actually make a classroom up on the roof. And then there's going to be a future rain garden for studies by Colleen Chan on removing particulates in the storm water, which she doesn't want there. So what that's going to look like is an area of the elevated lab of the 1,300 square meters, an area which is going to be limited to a maximum of 60 students on the roof at any one time, and they'll be secured with handrails. So the acknowledgements to this to date is obviously the whole of the School of Construction. The carpentry, steel fab, and plumbing have already come to the table in terms of helping to install the deck, build handrails, build the learning center, plumbing in the rainwater harvesting system. Campus planning has to be there as well, and the Factor 4 group has put in some capital money for this as well. And with that, I'll say thank you very much and take any questions.